Like you see in this example, as you can see, there's an image beneath. We are having in total 12 rooms. So the states corresponds to the location of the room, which will be representing using XY coordinates. So at this side, we are having X, this side we are having Y. So this room is 1, 1. Just a second. Similarly, this room is 4, 3. So these rooms would be representing a state. Now the actions, I can move up, I can move down, I can move left, I can move right to switch between the rooms. Then we'll be having a transition function, which tell us that if I am on a given state, if I take a action, I'm supposed to land in another state. And what is the probability that given the some initial state and some action over which you are moving to the next state, what is the probability for the switch? Okay, so as an example, as we have seen in the previous slide, that we will be dealing with a stochastic environment. So if we are moving in the direction of the desired action, then the probability is 0.8. If you move left or right to the desired action, it is 0.1. And I cannot move opposite, as its probability would be 0. Like if you see this first example, which says that previously I was in state 3, 3. So this state was your previous state. Maybe let me call it as S1 in this case. And next state would be 4, 3, S2. Okay. And let's assume for time being, the arrows that you see on the screen are the desired actions. Okay. It means for this switch, I'm supposed to move towards the right side. That is the correct action. But in this case, if you see over here, we are taking an up action. That means instead of moving towards right, I am moving upward. Now, what is the probability in this case? What is supposed to happen? Now, assume that you are standing at this position. Try to visualize this thing. You're standing at this position, looking in the direction of the desired action, which is this one. And stretch your arms. Now, while stretching your arms, standing at this position, looking in this direction, where do you see this direction? Is it in the same direction, or is it towards the left side, or is it towards the right side, or is it just the opposite side or the reverse side? You'll witness that while standing over here, looking in this direction, this action that you are supposed to take, which you have taken up, is looking like it is left to the desired. If you visualize by extending your arms, so if I'm moving left to the desired, the probability is 0.1. Okay, let's take another example. I am in state 3, 2. So the state that you are in is 3, 2, which is this one. So let's say in this case, this is your S1. And you are supposed to move in state 3, 3. So this is your S2. And the action that you are taking is up. So this is the action that you are taking. So you see that the action that you are taking is actually the desired action. So the actions match. So if you're moving in the desired direction, then the probability will be 0.8. Okay. The last couple was reward. So maybe reward for being in any non-final state. Like in this case, the final states were where +1 is written, which is 4, 3 and 4, 2. So these are the final states or deterministic states. So for if you land into these states, then the reward would be +1 and -1. Otherwise, being in any of the non-final state, the reward is supposed to be a small negative value which has been given here as -0.04. So this we can decide depending upon what situation we are in and what kind of problem we are trying to solve. We'll look into the reward aspect a little later. So this is how things are working. So it's like there is a robot trying to search for a jewel. There are certain locations which the robot would not like to be in. Like in this case, there's a fire in this room. If the robot goes inside, it will be destroyed. Here, obviously, if I am switching in the wrong rooms, I should be penalized. So accordingly, we are having a reward which is a small negative value, so that it keeps me on track. And this is how, if you see over here, if this is the robot over here, and if I try to take an action which is towards this room where fire is there, I will destroy it. If I move away from the fire, obviously I should be given would be giving the more probability, so that I should restrain myself into collapsing into a room where it is not suitable for me. Okay. Now, so as we said, the reward could be positive or negative. If it is positive, it is giving me an idea that I'm moving in the correct path. If it is negative, it is penalizing me so that I should change my path. So this reward could be based upon just a state. Like we have said, if we are in a given state, this is the reward. Or we can associate an action also. Let's say, if I am in a given state, if I take this action, now this will be the reward. It can be dealt that way also. Or the other way could be, what was your previous state, what action you have taken, and now you landed to some other state. So in this triplet sequence, what is the reward you want? Okay. For time being, just for the simplicity purpose, this lecture will only focus upon reward per state. This one. Now, then we have environment history. Obviously, what do we mean by it? The sequence of actions that we have taken so far. Okay. So the utility function is nothing but the sum of the rewards that have been received during the course of actions that you might have taken. You would be in one state, you got some reward, then you have taken another action, you were in the next state, you got some reward over that state, and so on. Okay. So if we take the previous example where the reward for reaching to the final state, which was a positive final state, was +1, and for any non-final state was -0.04. In that case, if we say that in 10 steps or 10 attempts, after taking 10 actions, we reach to the final state, then what is the total utility? Total utility is nothing but the sum of all the rewards that we have taken. So in 10 moves, after the 10th move, we reach to the final one. So this for the final one. So this is 1. Utility is 1. The reward was 1 over there. And for the other states, which before taking these 10 steps, so were non-final, and they are having the reward -0.04. So in total, we came to know that we made a profit, or we got a total reward or utility to be 0.6. Now, the idea here is, I do not know in which room there is a jewel, in which room we have fire. Am I moving away from the jewel, or am I moving towards the fire? We do not know anything. This can only be known if we have a map to solve this puzzle. So this map over here that you see on the right side is containing the correct action I am supposed to take if I am on a given state. So this is nothing but in terms of the solution of the Markov decision process, it is a policy. Okay, so we are interested in knowing this policy. So if the processes are deterministic, then the solution is a plan. Okay, what is the next step I should take? But since we are dealing with the stochastic environment, that too which is observable, so here we'll call this a policy. That I am on a given state, what is the correct action I should take? Obviously, for taking every action, there is some probability attached. And accordingly, we'll come up with the final solution. So here, the final solution is a policy, which is nothing but you are mapping a state with the action. Like at a given state, what is the action I should take? Okay. So initially, I can have some random values associated with the policy, and then we can update the policy depending upon if we got a better path. Okay. But what is the obvious need? What is the best policy or the optimal policy? One needs to worry about. If we know the policy, how to execute it, you will be in some initial state. You will look into the policy or that map. What is the action I am supposed to take on this initial state? I would be taking that action. I will land to some other state. Again, on that state, I look into the policy. What is the correct action I should take, and keep on updating until unless my problem is not solved. Now, what should be the optimal policy? Let's consider the example. Now, the concept of reward will come. If you see, there are two final states which are +1 and -1. +1 is a very high value, -1 is a very low, very negative. And we are picking the reward for every non-final state to be a very, very, very small negative, which is -0.04. So, what is the idea it is going to be? If I'm considering a very small non-final state reward to be a value which is very much closer to 0. If you see the arrows over there, what it is telling us is, like, if you consider this arrow, you might see over here that I'm not looking for a shorter path. Why are we moving towards the left side? Actually, we would have moved upwards. So in 3 moves, I would have reached to +1. But it is not moving upwards, rather it is moving towards the left side. Because the reward for being in a non-final state is very small, that I do not want to take any risk. The risk of being trapped in a -1 state. Because if I move up, there are chances that in this state X, I may take right path. What if on this state, if I take a right action, I'm trapped, everything is gone. Instead, I'm trying to move away from this negative state, even though I would be going along a very longer path. But if you see, the cost which has been incurred in every state is a very small. It's -0.04. It's a very small value. It will hardly affect my final answer. Okay. So here, the idea, what we are getting is, we are not ready to take any risk. Okay. Now, just try to think for this situation for a while. Now, for every non-final state, we are keeping a reward to be a very high negative, higher than -1, which was there. So what do you think should be the course of actions, the correct policy? Should I go for a larger path or a shorter path? Should I take the risk or not? Taking the risk is that it is okay for me to go towards -1 side. I'm ready to take my chances. If my probabilities are okay, I'll be able to move away from that -1 zone. What do you say? Let's try to think for a while. Let's see the solution. Now try to see the arrows. In this case, I do not want to look for a larger path. I want the shortest path. Okay. And even in this case, I'm ready to finish my problem, finish the solution by landing to -1 state. Why? Because reward for being in any other state apart from the final states, it is higher than -1. Okay, it's a higher negative value. So I would like to quickly finish the problem. Does not matter whatever be the exit route, whatever be the nearest exit route, I should finish now straight away. Okay, that's why if you see over here for this particular state, I am ready to finish in one step and go to -1. Otherwise, if I would have finished in +1, so I would have taken 2 steps. At this state, I'm having -1.6. At the above state, if I go, again it will be -1.6, then it will be +1. I'm ready. I'm not ready to take any chances. I want to finish it as soon as possible. Okay? Try to think for this scenario. Now, again, the reward for being in a non-final state is negative, higher one, but not higher than minus. But still it is higher thing. What do you say? What will happen in this case? Again, try to think for a while. Let's see. In this case, since the reward for every non-final state is smaller than -1, but still it is higher. So I would like to go for the shortest path first of all. I'm ready to take a risk, but I'll not try to finish the problem by landing to a -1. I'm ready to take my chances, ready to take the risk, but I'll go for the shorter path. Like if you see over here, for this state, I'm not willing to go for a longer path, because if I go for a longer path, the reward for being in a non-final state is still a little bit higher negative. So if there are more number of states, it will be more of the negativity added into the utility. Okay, so I'm ready to take my chances, but I'll go for a shortest path, and I will not finish with any nearest exit. Rather, I would like to finish only with positive one. Right? Now, this case, so this is similar to the one which was initially told, like it is -0.04. It is the same concept would apply. In this case, I'm willing to take a longer path, but I don't want to get trapped into -1. Here it says don't take any risk, move in the opposite direction of the negative states. Like in this case, if you see over here, this was -1. So these are the two rooms which are closer to this -1 state. So in the state, take an action which is just opposite to moving inside the room, which is where -1 is. Okay. Now the final case, rewards are positive. This is an interesting one. What do you say? What will happen in this case? Just think for a while. Okay. Now, what is happening? reward for being in any non-final state is a positive value. That means I would like to be always in the non-final state. I should take those actions which is taking me towards the non-final state only. That means I do not want to finish the problem, because if I finish, I do not have more moves. So here I would like to stay in the problem, or if this is a game, so I would like to stay in the game itself. I do not want to complete the game, because being in the game, I'm getting more profit since the rewards are positive. Let's see over here. So in this case, if you see, these are the two final states where my game will finish. And these states which are closer to these rooms are these three, where these three arrows are marked. I'm moving just in the opposite direction, so that I should not land inside the room. Okay. And if I'm on a non-final state, let's say if this is a non-final state, I can take any action. Either you take up, down, left, right. I still be in a non-final state. Here the idea is, if this is the reward you're supposed to take, in this case, you will like to be in the game, never finish. I hope now the concepts are being cleared. Like, what is the role of a reward corresponding to a non-final state? How it will affect the points? Okay.